So in the previous slide, we saw already one partial fraction expansion, and this is something that works more generally. So assume that our denominator, q of x, can be factored as q of x equal to x minus alpha 1, x minus alpha 2, all the way up to x minus alpha n. So in particular here we have that degree q is n, and we also, from this decomposition, we see that the alphas are basically the roots of q of n. And we have to make a special restriction. We also demand that all the alpha I are distinct. So where alpha I are distinct. And by the way, we also want them to be real. If that's the case, then we have the partial fraction expansion. We can write p of x divided by q of x as a sum a1 x minus alpha 1 plus a2 x minus alpha 2 and so on, plus a n x minus alpha n. And then how do you find these coefficients a1, a2, an? They're a priori indeterminate, so you can find a1, a2, and so on by adding fractions together and comparing with p of x. And then assuming that you found these a's, then what do you have for the integral? Well, then integral p over q is the integral of each of these little terms, and each term by itself will give you an ln if you integrate it, so you get a bunch of logarithms. a1 ln x minus alpha 1, a2 ln x minus alpha 2, plus dot dot dot, an ln x minus alpha n plus a constant. So let's look at an example. Let's look at the integral of x plus 2 divided by x cubed minus x dx. So x cubed minus x is x minus 1, x plus 1. So the roots are all distinct. We can use our partial fraction expansion, and we can write x plus 2, x cubed minus x as a over x plus b over x minus 1 plus c x plus 1. And now to determine the coefficients a, b, and c, we add the fractions back together. So we get a x minus 1, x plus 1, b, and then c x minus 1, x plus 1. So now if we simplify that, we get a plus b plus c x squared plus b minus c x minus a x minus 1 x plus 1. So now let's compare what we have on the left hand side here. So we have in particular no x squareds, so 0 times x squared. So this term as well has to be 0. And then we have 1x, so for that to match, this term has to be 1. And then last, the constant term is 2, so this has to be equal to 2. So from that we get minus a is equal to 2, b minus c is equal to 1, and then a plus b plus c is equal to 0. It's a system of linear equations that you can solve. In particular, you see that a is equal to minus 2. And if you solve the system, you should also find that b is 3/2 and c is 1/2. Okay, so with these coefficients, we can go back to our original integral, and we can use the partial fraction expansion to write this as minus 2 integral dx over x plus 3 over 2 integral dx x minus 1 plus 1/2 integral dx x plus 1. And those forms I know, so I get ln of x, 3/2 ln x minus 1, 1/2 ln x plus 1 plus a constant. So now there's a special case that wasn't comprised in our original theorem for the partial fraction expansion. So it can be, we started from saying that q of x has to be written as a product of linear factors. But we know from our fundamental theorem of algebra that this is not always possible. It's possible that there's an irreducible quadratic factor as well. So we could have things like q of x is x squared plus 1. You can't write that as the product of two linear polynomials unless you use complex numbers, but here we want real numbers. So this is an irreducible quadratic factor. So in particular, you have no real roots. So in that case, what do you do if you have these irreducible quadratic factors? Well, here you will get a linear term in the numerator. So let's look at an example. Let's look at the integral of x plus 2 and now x cubed plus x dx. So compared to the example on the previous line, we have a plus here. And so x cubed plus x is x squared plus 1. And so once again, this is a irreducible quadratic factor. So there's a partial fraction expansion for these kind of expressions as well, but it's a little bit more involved. The partial fraction expansion tells you that you can write the rational function as something over x, because that's just a linear term, and then plus something for a quadratic factor, x squared plus 1. And here we have to put a linear term, so bx plus c. So this is the new thing here. And now finding the coefficients is, again, the same principle as before. We just add the fractions back together and compare terms. cx plus a x squared plus 1. Again, we have no x squares here, so this term has to be 0. We have one x term, so c has to be 1, and the constant term is 2, so a here has to be equal to 2. And so our system is now a very simple one. A is 2, c is 1, and a plus b is 0, so b is minus 2. So now for our integral, what does that mean? We can write it as 2 times 2 over x plus minus 2x plus 1 divided by x squared plus 1, and that all times dx. Now we can pull that apart a bit more to write 2 dx over x minus 2 x dx x squared plus 1 plus integral dx x squared plus 1. So I'm going to continue below here. So now I have things that I know. Integral of 1 over x is ln absolute value of x. I've done it a couple of times now. Minus 2. This is one of my special forms that I derived earlier. And this is going to give me a 1/2 ln absolute value x squared plus 1. And then last, this is also a special form, or you recognize this as inverse tan of x plus c. And now the only thing that you can do, just a small detail, is you can simplify these two terms, and you're left with 2 times ln absolute value x minus ln x squared plus 1 plus tan inverse. There's another special case now that we have to look at. So again, in our original partial fraction expansion, we said, okay, we want Q to be this product of linear terms, and we want all the alphas to be distinct. So now the question is, what do we do if we have repeated factors? So what if not all of the alphas are distinct? So here what we're going to do is we're going to assume that Q of x has a repeated factor So in particular, we'll take Q of x to be x minus alpha to the power m. Then what we can conclude from that is that our partial fraction expansion will have m terms, and they correspond to increasing powers of m. So we'll have a times x minus alpha plus b x minus alpha squared plus dot 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 all the way up to the end. Let's call this a1, a2, am x minus alpha to the power m. So as many as the exponent that you have factors for. And again, to compute the coefficients, you add the fractions together again, you expand and you compare the coefficients. Now you might wonder, well, what if I have repeated and single factors and quadratic factors? Well, that's not a problem. If you have more factors here, let's say x minus alpha 2, x minus alpha 3, let's say, dot dot dot, then you just get more terms in your partial fraction expansion. Bx minus alpha 2, Cx minus alpha 3, and so on. And if you have to boot a quadratic term, so let's say x squared plus ex plus f, irreducible, then you also get a term rx plus s divided by x squared plus ex plus f. So all of these things add together. So let's do a small example, and then I'll give you another fraction. I'll give you another one to try out. Actually, I'll write this example down without working through the steps. So for partial fraction expansion, have a look at 1 over x squared x minus 1 to the power 3. So according to the rule, we have two roots here, 0 and 1. 0 has multiplicity 2, 1 has multiplicity 3. And so our partial fraction expansion becomes a over x, b over x squared, plus cx minus 1, d x minus 1 squared, e x minus 1 to the power 3. If you add this together and you solve the system for a, b, c, and d, it's a bit of a calculation, but you will find that a is equal to 3, b is minus 1, c is 3, d is minus 2, and e is 1. So you can check this by yourself. For this example, we'll look at the following integral of dx divided by x to the power 3 minus 5x squared plus 8x minus 4. And let's first look at the denominator. Then what we see is that x is equal to 1 is a 0 of this polynomial. So we can decompose q of x as x minus 1 and then times a quadratic polynomial, and to find out what the remainder is, you have to do a quick synthetic division. So we do 1 minus 5, 8 minus 4, and then the 1 from the root that we already found. And we calculate 1 times 1 is 1, minus 4, minus 4, 4, 4, 0. So the remainder is x squared minus 4x plus 4. So the quotient after division is that polynomial. And so we have that q of x decomposes as this polynomial, and then x squared minus 4x plus 4. Either you look for roots manually, or you observe that this is equal to x minus 2 squared. So this whole thing, x squared minus 4x plus 4, that is equal to x minus 2 squared. So here we're in the situation where we have a single root, or a root with multiplicity 1, and a double root, x is 2, with multiplicity 2, because the exponent here is 2. So for the partial fraction expansion, that tells us the following. We have 1 over the denominator is equal to some coefficient a, x minus 1, plus b divided by x minus 2, plus c, x minus 2 squared. That's the form that we need. And now we can bring it all on the same denominator, and we get a times x minus 2 squared plus b x minus 1 x minus 2 plus c x minus 1 divided by x minus 1 x minus 2 squared. And now we expand all of these factors in the numerator, and we collect terms in x squared, where we get a plus b x squared, and then plus negative 4a minus 3b plus cx, and last but not least the constant term 4a plus 2b minus c, and all of that divided by x minus 1 x minus 2 squared. And so now if we compare the numerators, so we have to have that whatever we write on the right hand side here has to be equal to 1. So we see that the first coefficient has to be equal to 0, the coefficient of x squared. Likewise, the second coefficient of x has to be equal to 0. And then finally, the constant term has to be equal to 1. And that gives us the following set of equations for a, b, and c. So a plus b is 0, minus 4a minus 3b plus c is equal to 0, and 4a plus 2b minus c is equal to 1. And so now you can solve that set of equations for a, b, and c. I will not do that explicitly since it's quite a straightforward set of equations, but you should get that a is 1, b is minus 1, and c is equal to 1 as well. And from that, from this it follows that our integral, so let's call it I here, the integral that we wanted to calculate. Our integral is the integral of the partial fraction expansion, so integral dx x minus 1 minus integral dx x minus 2 plus integral dx x minus 2 squared. And now these subintegrals are easy to calculate and give you logarithm of absolute value x minus 1, logarithm absolute value x minus 2, minus 1 over x minus 2 plus a constant. And so where does, just one last thing, so where does this integral expression come from? It comes from the fact that our partial fraction expansion tells us that 1 over x to the 3 minus 5x squared plus 8x minus 4 is equal to, substitute the coefficients, it's 1 over x minus 1 minus 1 over x minus 2 plus 1 over x minus 2 squared. And so finally we end up with our result, which is given down below.